We're going to start off by talking about a bunch of limit laws. So today we're talking about, we're starting to figure out limits, not based on graphs, not based on tables or plugging in values, based on just given the function, the equation. Okay, let me go over some of these laws. You don't need to write much down, but and we'll refer back to these many times. Just let me give you a rough idea what it is. So the first one, the limit of the sum of two functions. We can find each limit separately. The limit of f plus the limit of g. So the limit of a sum is the sum of limits. For the first five, this is only true if the actual limits exist. They equal some number, equal some other number. Okay, if one of the two does not exist, the law does not apply. Okay, and then the difference, the limit of the difference is the difference of limits. Okay, anytime you have a constant in front of a function, we can bring that outside the limit. So for example, the limit as x goes to 5 or something of 7 times the square root of x plus 3. I'm just making some up. If we want to, we can just bring this guy outside. 7 times whatever the limit is. Okay. Number 4, the limit of a product of two different functions is the product of the limits. So for example, the limit as x goes to 0 of rad x times e to the x. Anytime you have a product, it's equal to the limit of the first function times the limit, whatever the second function is. Again, that's only true if this equals some number and this equals some number. The limit of the division of two functions is the division of the limits. This is only true if both of them equal some number and the bottom one does not equal 0. Okay. Now this one, if we have some function to any power, for example, the limit as x goes to 2 of the fifth root of 4 to the power of x, really. Oh, that's not the best example. Let me go with cosine of x. Where the fifth root is what power?
1/5.
1/5 power. So that's the fifth root or 1/5 power of the limit. Okay. Number 7, the limit of a constant is just equal to the constant. Why is that? All right, we have some constant function. No matter what x is, so whatever a is, as you approach a from the left and the right, it's always equal to whatever that constant is. It is whatever that number is. Don't worry about 8 for right now. Let's skip the next few. Let's turn to the backside. It says if f is a polynomial or rational function, and a is in the domain, all you have to do is directly substitute in that number into the function. We talked a little bit about this last Wednesday. Why can we do that? But yes. This is continuous everywhere. This is continuous on all members of its domain, everything except what makes the denominator 0. So in fact, we're going to use direct substitution, not only for polynomials and rational functions, any continuous function. Which are all the functions you know. Polynomials, rational functions, exponential functions, logarithmic functions, all trigonometric functions. As long as that a value is in the domain, we just directly substitute it. Okay. And then we'll go over these last two some other day. So, all right. Let's call this tricks for any limits. And we're going to have a big list. Okay, so leave a lot of room and then maybe start working on the examples on the next page. Number one trick is direct substitution. In fact, this is almost always how we start every limit. Okay, so we try plugging in the value we're approaching. What type of function is this? Rational. We really don't even need to identify as rational for right now, but we always just try plugging in the number 3. I do it on the side somewhere. 3 squared minus 4 over 3 minus 2. What is that? 9 minus 4 is 5 over 1 is 5. If you end up with a number, that is the limit. Okay? Done. Easy peasy. Okay? Why does this work? As long as this number is in the domain of a continuous function, just directly substitute. The limit from the left, always leave the limit from the right will equal the function value. Okay? So that's the first trick. Next example. So this is the same function, but now we're approaching it. We're approaching as x goes to 2. Again, on the side, we always try direct substitution. 2 squared minus 4 over 2 minus 2. And we get 0 divided by 0. What is 0 divided by 0? It's not a number. Okay. However, this is very important. Anytime when you do direct substitution in a limit, in terms of a context of a limit, this is called an indeterminate form. Okay. Why is it called an indeterminate form? Anybody want to take a guess? Because we cannot determine what the value of the limit is. The limit might exist, the limit might not exist. We cannot determine that yet. So anytime you get 0 over 0 in indeterminate form, okay, and it means we got to do more work. Anybody know the trick for this one? Okay, we try factoring.
In fact, every time you get 0 over 0, that almost always means x minus this number is both a factor of the numerator and denominator. Okay. And once you factor it, we should see this common factor. Okay. We're going to simplify it. Although before I do that, let me ask you this. If you're just given this function, are we allowed to just simplify it? This function? Are they the same function? Is this function the same as this function? Definitely not. They're way different functions. Okay. Well, not way different. This function has a hole in it. This function does not have a hole. Okay. So if you're just given a rational function, you can't just simplify. That changes the function. We've got rid of the hole. Totally different function. However, right, as long as x is not equal to 2, they are exactly equal. We agree with that? No matter what number you plug in, like we did 3 last time. 3 minus 2 over 3 plus 2 over 3 minus 2. All these happen to be 1, but this number is always simplifies to this number, as long as x is not 2. So these are the exact same functions, however, are everywhere except at the value x equals 2. So why can we simplify inside limits? Okay, so we are going to simplify and say that this is the limit as x approaches 2 of x plus 2. The reason we could do that inside of a limit is because when we're approaching 2, we don't care what happens at 2. All we care about is what's happening from the left and from the right. Okay? Since we're approaching 2, we're never equal to 2, so these are always exactly the same number, and we can simplify it. So inside limits, common factors, we can simplify it. And then we go back to our previous trick, which is what? Direct substitution. So we plug it in, and we get 2 plus 2, and the answer is 4. Okay, so trick number 2 is factor and simplify. Okay, and we often do this trick when you end up with 0 over 0. What's the first step we always do? Direct substitution. And again, I do it on the side. Get 5 over 3 minus 3. And again, direct substitution, doesn't matter if we're going from the left or the right. And we get 5 over 0. Is this an indeterminate form? This is not an indeterminate form. Okay? Anytime you have any number other than 0 divided by 0, it's not an indeterminate form. Not indeterminate. Okay? Whenever you get a number over 0, the answer is either going to be infinity or negative infinity. Okay? Here, this rational function has a vertical asymptote at 3. Once we know it's a number over 0, we now just have to determine which one it is, positive or negative infinity. And how do we figure that out? How do we know if it's going up or down? Or just plug in a number very close to 3, but from the left, which would be what? 2.9. 2.9 is fine. 5 divided by 2.9 minus 3. And all we care about is the sign. Is it positive or negative? 5 divided by negative 0.1. Is this positive or negative? Definitely negative. So what does that tell us? The answer is negative infinity.
So again, anytime you direct substitution, you get a number over zero, the answer is going to be either positive or negative infinity. Okay? Sort of.
That's when it's going from the left to the right. If it was this question, the limit as x goes to 3 of 5 over x minus 3.
Okay. This is not from the left or from the right, it's from both. And now we have to check both sides. If they both go to negative infinity, the answer is going to be negative infinity.
So here we just have to check what is the limit as x goes to 3 from the right. Again, you substituting, you get 5 over 0. So we just have to determine, is it positive or negative infinity? And we just plug in a number to the right of 0. So 5 over 3.1 minus 3. 5 over 0.1 positive. Since it's positive, this limit is equal to positive infinity. So what is the limit as x goes to 3? Does not exist. From the left, it went to negative infinity. From the right, it went to positive infinity. So this does not exist. So let's write down this trick. Not really a trick, but if you get, by direct substitution, a number divided by 0, non-zero number, the limit will either equal positive infinity or negative infinity, or does not exist.
You got to check both the left and the right. 0 over 0, indeterminate form. Any number divided by 0 is not indeterminate. The answer is either positive or negative infinity, or from the left and the right, they're opposite. It does not exist. Okay, what's the first thing we always try?
Direct substitution. Add 9 minus 3 over 9 minus 9. And we get 0 over 0. And what do we call that? Indeterminate form. Okay, so it means we gotta do some other work. Okay. Anybody know the trick for this one?
Multiply by the conjugate.
Okay, so we're going to multiply by the conjugate of either the numerator or the denominator. Okay. When do we do this trick? Typically, you got to have two different terms. Okay. Both of them have two terms, but especially when it involves a square root. Okay. So we're going to multiply the numerator and denominator by the conjugate of one of them. This case can be the conjugate of the numerator plus 3 with the limit as x approaches 9. X plus 3 x minus 3 x minus 9. Okay. The other thing is don't distribute the denominator. Just leave it the way it is. X minus 9 rad x plus 3. We really only distribute the side that, or the either the numerator or denominator that who we chose the conjugate of. And when you multiply conjugates, the two middle terms always add to be 0. So we get the limit as x approaches 9, x minus 9 over x minus 9. And now what? Okay, if you try plugging in 9 again, direct substitution, you still get 0/0. However, we go back to our previous trick. Most of the time, you get 0/0. We have a common factor. In this case, we have a common factor of x minus 9. We do simplify. We try direct substitution now. We get 1/6. Okay, so let's call it trick number 4. Okay, so we're going to multiply the numerator and denominator by the conjugate of either the numerator or the denominator. Okay. And when do we do this? Typically when there's square root and 2 terms in either the numerator or denominator. If we try direct substitution here, we get 3 plus 0 to the negative 1 power minus 3 negative 1. We get 0/0. What are we going to do here? Okay. What does this mean to the negative 1 power? 1 over. So this is okay. Yes.
Wait, this is the negative 1 power. Would that make it negative 1/3?
No. To the negative 1 power simply means 1 divided by whatever it is.
Just the reciprocal of whatever's inside that exponent. Okay. So here we got fractions inside of fractions. Sometimes we call that complex fractions. Not like a complex number, just fractions inside fractions. So our trick is just to make one fraction. We don't want fractions inside of fractions. So we got to get a common denominator. So multiply this by 3 plus x over 3 plus x. Multiply this by 3 over 3. Minus 3 plus x over 3 times 3 plus x over x. Now we have one fraction divided by another fraction. Put that there. So we take the numerator, which if we distribute this becomes -3 minus x. And the 3 minus 3 is 0. So we got x over 3 plus x. And we multiply by the reciprocal of the denominator. That's what division is. And then what happens? We have a common factor. So it simplifies. Now we directly substitute in.
And when do I stop writing the word limit or lim? We stop writing when we actually find the limit or take the limit. So I did right here. Now I'm going to directly substitute it, and I got a number. Okay, this is when we don't write the word limit anymore, because we say we took the limit. The limit as it approaches is this. Everywhere else, we got to be writing the word limit
As x approaches whatever. So there it is. This is 1/9. So let's call this trick 5. Simplify complex fractions, which are fractions within fractions.